A moon is running away from home. It has broken the ancient bond with its planet and is now drifting alone around its star, a celestial orphan astronomers call a Ploonet. This is not science fiction, but a serious and stunning possibility in our galaxy. By the end of this, you will understand the cosmic forces that can tear a moon from its world and how finding one would rewrite the rules of planetary science. We will explore how a Ploonet could form in the chaos around a gas giant, what strange fates await it, and whether our own moon could ever attempt such an escape. What does it mean for a world to have no home? This cosmic orphan has a name, a Ploonet. The word itself is a simple blend, planet and moon, but the reality it describes is anything but simple. A Ploonet is exactly what we have been discussing, a former moon that has escaped the gravitational pull of its parent planet. Through a series of gravitational nudges, tidal forces, or a dramatic close encounter, it breaks free. It does not go wandering into the dark interstellar void, however. Instead, it gets promoted in a sense. It leaves its planetary orbit and enters a new, wider path, one that goes directly around the star. It transitions from being a moon of a planet to becoming an independent world orbiting the sun. To understand its unique place, we need to see what it is not. A Ploonet is not a rogue planet. A rogue planet is a world that formed around a star but was violently flung out of its solar system entirely, doomed to drift forever in the cold darkness between stars. A Ploonet, by contrast, stays in the neighborhood. It remains a member of its original star system, just with a dramatically changed social status, and it is certainly not a regular moon anymore. That relationship is severed. The Ploonet no longer circles a larger world. It no longer experiences the regular eclipses and tidal forces from a planetary companion. It stands alone under the light of its sun, a solitary sphere with a past it can never truly escape. This is the strange hybrid identity of a Ploonet, a celestial body caught between two definitions, forever marked by its great escape. The bond between a planet and its moon is one of the most elegant dances in the universe. It is a perfect dynamic balance between two powerful forces. The first is gravity, the relentless pull of the planet, constantly trying to draw the moon inward. The second is the moon's own inertia, its momentum carrying it forward in a straight line through space. Put these two together and you get an orbit. The planet's gravity acts like an invisible tether, forever bending the moon's path into a circle or an ellipse. It is like swinging a ball on a string around your head. Your hand pulls the string inward while the ball's motion tries to fly away. The result is a stable, circular path. For billions of years, our own moon has performed this dance with Earth, held in that exquisite tension between falling and flying. But this cosmic ballet has more subtle moves. Over immense stretches of time, a moon often becomes tidally locked to its planet. This means the moon's rotation on its axis slows until it matches the time it takes to complete one orbit. The result is that the same face of the moon always points toward its planetary partner. Our moon is tidally locked to Earth. We only ever see one side of it from our planet. This locking is a signature of a long, stable relationship, a sign that the dance has settled into a predictable rhythm. Sometimes the dance involves multiple partners in a phenomenon called orbital resonance. Imagine two moons orbiting the same planet. If the orbital periods of these moons form a simple ratio, like one moon completing exactly two orbits for every one orbit of the other, they can gravitationally nudge each other in a stable, repeating pattern. This resonance can keep their orbits orderly, like two dancers moving in sync, their steps perfectly timed so they never collide. This delicate gravitational choreography is what makes planetary systems stable. It is a system of checks and balances written in the language of physics. But what happens when the music changes, when a new force enters the room and upends this ancient, carefully balanced dance? Gravity's elegant dance is not always a permanent arrangement. That stable orbit, that perfect tension between pull and momentum, can be shattered. To break free, a moon needs a conspirator, a third force to disrupt the delicate two-body system. Often, that conspirator is the star itself. Even from a great distance, the star's gravity exerts a tiny, constant tug on the moon. This creates a complex three-way gravitational struggle. Over millions of years, these subtle stellar tides can act like a steady, gentle push, slowly transferring energy to the moon and causing its orbit to expand, moving it farther and farther from its planet. It is an incredibly slow process, a cosmic game of inches played over eons, but the destination is critical. Every planet has a zone of gravitational control, a bubble in space where its pull is stronger than the stars. Astronomers call this the Hill sphere. Picture a planet sitting at the center of its own sphere of influence. Inside this bubble, objects like moons are securely bound to the planet. But the edge of this sphere is a frontier. If a moon's expanding orbit carries it beyond this boundary, it crosses a point of no return. At that moment, the star's gravitational influence becomes stronger than the planet's. The moon is no longer a satellite. It has been gravitationally adopted by the star and begins a new life as an independent Ploonet. This tidal nudging is the most gradual path to freedom, a slow-motion escape. But there are far more violent possibilities. A close encounter with another massive object, like a passing star or a rogue planet hurtling through the system, could deliver a sudden, catastrophic gravitational kick. This cosmic billiard shot could instantly fling a moon out of its stable orbit, either ejecting it from the system entirely or tossing it beyond its planet's Hill sphere in a single, chaotic event. Alternatively, within a crowded system of moons, complex gravitational resonances could build up over time, not to stabilize but to destabilize. One moon might transfer so much orbital energy to another that it pushes its sibling right out of the family. The escape mechanism dictates the Ploonet's fate. A slow, tidal departure might leave it in a relatively calm, circular orbit. A violent ejection could send it careening on a wild, elongated path, a permanent reminder of its traumatic birth. So we have our escapee, a world adrift between identities. But what happens next? What does life look for a moon that has lost its planet? Crossing the Hill sphere boundary is only the beginning of its journey. The moon is now free from its planetary parent, but it is not yet settled. It has entered a phase of profound instability, a great migration from one gravitational master to another. Its old orbit, a tidy loop around the planet, is instantly erased. What replaces it is not a clean, circular path around the star, but something far more wild and unpredictable. The Ploonet's new orbit is often highly elliptical, a stretched oval that brings it swinging wildly between two extremes. At its closest approach to the star, it roasts. At its farthest point, it freezes. This elliptical path is a cosmic fingerprint, evidence of the violent or complex gravitational interactions that set it free in the first place. It is the orbital equivalent of a wobbly gate, a sign that this world is still finding its balance. Furthermore, its orbit is frequently inclined. It does not travel neatly along the same flat plane as the planets. Instead, it loops above and below the solar system's main disk, like a child skipping across the grooves of a record. This tilt is another clue to its chaotic origin, suggesting it received a gravitational shove from an angle, knocking it out of the orderly plane where it was born. This transition period is a time of extreme danger. The Ploonet is a new and unpredictable mass moving through a system that was balanced without it. Its chaotic, elliptical path can cross the orbits of established planets and asteroids. For a time, the inner solar system becomes a shooting gallery. The Ploonet itself is at risk of a catastrophic collision with another world, an event that would leave both bodies shattered. More likely, its gravitational influence acts as a cosmic wrecking ball. As it passes near other objects, it can perturb their orbits, nudging asteroids into new, dangerous paths or even destabilizing other moons. It is an agent of chaos. In some scenarios, this dance of destruction does not end well for the Ploonet either. A close encounter with a giant planet like Jupiter in our own system could give it a second, even more powerful gravitational kick. This slingshot effect could accelerate the Ploonet to escape velocity, flinging it out of the star system entirely. Its brief independence would end in eternal exile, transforming it from a Ploonet into a true rogue world, destined to drift alone in the interstellar dark. The Great Migration is a perilous trial. Only the lucky or the resilient survive it to find a stable, permanent orbit. So, if these objects are so chaotic and potentially destructive, how could we ever hope to find one? The search requires looking for celestial bodies that simply do not fit in. The hunt for these celestial runaways began with a puzzle. Astronomers staring at data from distant star systems kept finding planets that did not make sense. Some were far too large for their orbits, others had bizarre, tilted paths, and a few seemed to be disintegrating before their eyes. The standard models of planet formation struggled to explain these oddballs. So a team of scientists asked a radical question. What if some of these strange objects were not planets at all, but something else entirely? In 2019, astrophysicist Mario Susaquia and his colleagues at the University of Antioquia in Colombia proposed a groundbreaking answer. They gave a name and a rigorous scientific framework to the idea we have been exploring. They formally introduced the concept of the Ploonet. Their study was not just a flight of fancy, it was a detailed computer simulation. They modeled what would happen to large moons orbiting gas giant planets that migrated very close to their stars, a scenario we know is common in other solar systems. The results were astonishing. Their simulations showed that under these intense conditions, moons could indeed be stripped away from their planets, becoming independent star-orbiting bodies. Susaquia's team realized these escaped moons could solve multiple mysteries at once. A Ploonet drifting too close to its star could have its icy surface vaporized, creating a giant, dusty tail. This might explain the perplexing observations of some exoplanets that appear to be surrounded by clouds of debris, as if they are slowly evaporating. Furthermore, the gravitational departure of a large moon would violently jolt the parent planet, potentially knocking it into a tilted or highly elliptical orbit. This single, elegant idea could account for two different classes of bizarre exoplanet data. The motivation was clear: to make sense of the chaos. By proposing the Ploonet hypothesis, these scientists provided a new lens through which to view our increasingly strange galaxy. They argued that if their models were correct, Ploonet should not be rare flukes. In solar systems packed with gas giants, the dynamic processes that create them might be commonplace. The galaxy could be teeming with these orphaned worlds, each one a silent testament to a violent gravitational past. Their work transformed a speculative notion into a legitimate, testable theory in astronomy. It gave researchers a specific new thing to look for in the mountains of data from telescopes like Kepler and TESS. The search was no longer for generic oddities, it was for the specific signatures of a moon that had run away from home. The strange world of WASP-12b is a cosmic horror story. This exoplanet is a gas giant, a so-called hot Jupiter, orbiting so close to its star that a full year there lasts just over one Earth day. It is being actively consumed, its atmosphere boiling away into a vast, comet-like tail as its star strips it apart. But the true mystery is its orbit. WASP-12b is spiraling inward on a decaying path that will eventually lead to its destruction. This death spiral defies easy explanation, and here is where the Ploonet hypothesis offers a chilling possibility. What if WASP-12b is not a traditional planet at all, but a Ploonet that escaped a larger gas giant only to meet a terrible fate? The idea is this: imagine a system with two gas giants. A larger world holds a massive moon. Through gravitational interactions, that moon breaks free, becoming a Ploonet in an elliptical orbit. But its new path is a dangerous one, swinging it perilously close to the star. Each close pass drags on the Ploonet's atmosphere and tugs at its orbit through intense tidal forces. Over millions of years, this drag decays its orbit, tightening the spiral of doom. This scenario could elegantly explain both the planet's extreme closeness to its star and its observed inward migration, a migration that is unusually fast for a typical planet. Furthermore, the violent process of escaping its original planet could have left WASP-12b with a puffed-up, unstable atmosphere, making it even more vulnerable to the star's relentless stripping. While not yet proven, this theory turns a perplexing anomaly into a potential case study. It suggests we might be witnessing the final, tragic act of a moon's great escape, a Ploonet that found freedom only to fall into a gravitational furnace. The debate continues, with other scientists proposing different mechanisms, like interactions with a hidden companion planet. Yet the Ploonet model persists because it connects so many bizarre dots with a single, dramatic story. It forces us to ask how many other doomed worlds in our galaxy began their existence as moons. Finding a Ploonet is like searching for a single, dim light in a stadium of spotlights. The challenges are immense. These are not giant, blazing stars or even Jupiter-sized planets. A Ploonet would be a relatively small, cold, and dark world, especially if it has wandered far from its star. It does not generate its own light. It only reflects the faint glow of its sun, and from the incredible distances of interstellar space, that reflected light is vanishingly weak. Its small size makes it even harder to spot against the overwhelming brightness of its parent star. So how do we hunt for something that actively avoids being seen? Astronomers must become cosmic detectives, looking not for the object itself, but for the subtle shadows and disturbances it leaves in its wake. The most promising method is the transit technique, the same workhorse that has discovered thousands of exoplanets. Here, telescopes stare at a star, meticulously measuring its brightness. If a Ploonet passes directly between that star and our telescopes, it will block a tiny fraction of the starlight, causing a brief, periodic dip in brightness. For a Ploonet, this dip would be exceptionally small, a faint whisper in the data, but the real clue would be in the timing. This dip would not follow the regular pattern of the known planets in that system. It would appear at irregular intervals or on a wildly elliptical path, a signature of an object that does not belong to the orderly planetary family. Finding that anomalous, repeating blip in the light curve would send astronomers into a frenzy of analysis. Another possibility lies in the Ploonet's past. If the escape was violent, or if the Ploonet is a fragile icy body now drifting close to its star, it might be surrounded by a vast cloud of dust and gas, the remnants of its evaporating surface. This debris disk or cometary tail would be much easier to detect than the Ploonet core itself. It would scatter the star's light in distinctive ways, creating a hazy, extended signature. We might spot the ghostly shroud of a disintegrating world long before we confirm the solid body at its heart. In the far future, next-generation telescopes with incredibly powerful coronagraphs might be able to block the star's glare directly and take a picture of the Ploonet itself, a faint dot of light swimming in the darkness. But for now, we rely on these indirect fingerprints. The monumental importance of such a discovery cannot be overstated. Confirming the first Ploonet would do more than just add a new category to our celestial catalogues. It would be a direct validation of the dynamic, often violent processes that shape solar systems long after they form. It would prove that moons are not permanent fixtures, but temporary companions in an ever-changing gravitational landscape. A Ploonet would be a frozen record of its own traumatic history, its orbit a map of the gravitational chaos that created it. By studying its composition, we could learn about the conditions inside the circumplanetary disk where it was born, offering a unique window into the birth of moons around giant planets. Finding one would force us to rewrite the textbooks, blurring the line between moon and planet forever. It would tell us that our galaxy is not just a collection of stars and planets, but a graveyard of broken orbits and escaped worlds, each with a story of a great gravitational divorce. And that realization leads to a haunting question closer to home. Could our own familiar moon ever attempt such a dramatic escape? Our own moon provides a perfect test case for this cosmic drama. It is slowly, inexorably moving away from Earth. This is not a theory, but a measured fact. Astronauts from the Apollo missions left reflective panels on the lunar surface, and by firing lasers at them and timing the light's return, we have tracked the moon's retreat with millimeter precision. Each year, the moon drifts about 3.8 centimeters farther from our planet. The mechanism is tidal friction. Earth's oceans bulge slightly toward the moon, and as our planet rotates faster than the moon orbits, this gravitational bulge is pulled slightly ahead. This tug pulls the moon forward in its orbit, giving it a tiny boost of energy that pushes it into a higher, slower path. It is the same gradual process that could, over eons, lead to escape. But here is the crucial point: our moon will never become a Ploonet. The reason is the sun. Long before the moon could drift to the edge of Earth's hill sphere, the dynamics of our entire solar system will change. In roughly 5 billion years, as the sun swells into a red giant, its changing gravity will fundamentally alter the orbits of every remaining body. More immediately, the sun's own tidal influence on the moon's orbit is actually working against its escape in a complex balance that will likely stabilize the retreat long before freedom is possible. So, while the moon is indeed leaving us, it is a leisurely, billion-year farewell, not a dramatic breakout. Its fate is to remain a loyal companion until the sun's final acts rewrite the entire system. This stability, however, is not universal. In other solar systems where gas giants orbit blisteringly close to their stars, the tidal forces are monstrously stronger, and the hill spheres of those planets are dramatically smaller. In those extreme environments, the process of lunar escape can be compressed from billions of years to mere millions. Our peaceful celestial neighborhood is the exception, not the rule. So what becomes of a world that has abandoned its home? A Ploonet's independence is often a fleeting chapter in its long life, a temporary state of chaos between two more permanent fates. Its destiny is not written in the stars, but in the cold mathematics of its mass, its speed, and the gravitational landscape it now navigates. One of the most dramatic ends is a fiery return to the cosmic forge. If a Ploonet's escape leaves it on a highly elliptical orbit that dips extremely close to its star, each close pass acts like a gravitational brake. This process, called tidal circularization, slowly saps the Ploonet's orbital energy. Over millions of years, its wild, oval path shrinks and tightens, drawing it ever closer to the stellar inferno. Eventually, it crosses a point of no return, the Roche limit, where the star's tidal forces become stronger than the Ploonet's own gravity. The world is literally torn apart. It might be vaporized completely, or its shattered remains could spiral into the star in a final, brilliant shower of debris. This is likely the fate awaiting worlds like the hypothetical Ploonet version of WASP-12b, a tragic end to a grand escape. Alternatively, the Ploonet might not fall inward but be thrown outward with even greater violence. Its chaotic path through the inner system makes it a prime target for gravitational slingshots, especially from giant planets. A close encounter with a gas giant can act as a cosmic catapult. If the Ploonet swings behind the planet in its orbit, the planet's gravity can accelerate it tremendously, flinging it away at a speed greater than the star's escape velocity. In an instant, the Ploonet status changes again. It is no longer a Ploonet, but a rogue object banished from its native solar system entirely. It would become a dark, frozen wanderer drifting through the interstellar void, its only warmth the residual heat from its core, its only light the distant pinpricks of galaxies it will never approach. This is a fate of profound and eternal loneliness. For other Ploonets, the journey ends not with a star or an exile, but with a crash. The inner solar system is a crowded place. A Ploonet on an inclined, elliptical orbit is like a bullet crossing a busy highway repeatedly. The odds of a direct collision with a planet or a major asteroid are low, but over billions of years they are not zero. Such an impact would be cataclysmic for both bodies, potentially creating a new debris ring around the star or coalescing into an entirely new, hybrid world from the molten remains. The scarred surfaces of Mercury, Mars, and our own moon are testaments to a violent early solar system, a time when such colossal collisions were commonplace. A Ploonet impact would be a throwback to that primordial chaos. Yet there is a fourth, more peaceful possibility. Through a series of gentler gravitational nudges, perhaps from other planets or leftover debris in the system, a Ploonet's orbit could gradually circularize and stabilize over eons. Its wild swings could calm, its inclination could flatten, and it could eventually settle into a serene planetary orbit around its star. In this scenario, the Ploonet completes its transformation. It sheds its chaotic past and becomes, for all intents and purposes, a regular planet. Its origin as a moon would be buried deep in its orbital mechanics, a secret only the most sophisticated models could uncover. The factor deciding between these fates is often the Ploonet's initial velocity after escape. Too little speed and it falls toward the star, too much and it risks ejection. Just the right amount, combined with fortunate gravitational interactions, might allow it to find a stable niche. Its mass matters too. A more massive Ploonet has a stronger gravitational presence, making it harder to eject but also a bigger target for tidal forces. So the Ploonet story is ultimately one of gravitational chance, a cosmic lottery where the prize is either annihilation, exile, collision, or a quiet, hard-won stability. The fate of our own moon reveals the fine line between a slow retreat and a true escape. While it is drifting away from Earth, this movement is part of a delicate gravitational balance, not a prelude to a dramatic breakout. The mechanism is the same tidal force we see in potential Ploonet systems, but here the story has a different ending. Earth rotation transfers a tiny bit of energy to the moon through the gravitational drag of our oceans, pushing it into a wider orbit by a few centimeters each year. It is a glacial but measurable departure, yet escape requires crossing a critical threshold, the edge of Earth's gravitational sphere of influence, our Hill sphere. This boundary lies nearly 1.5 million kilometers away. Calculations show the Sun's gravity will disrupt the Earth-Moon system long before our satellite reaches that point. In roughly 5 billion years, as the Sun evolves, the delicate orbital dance will be irrevocably altered. So our Moon's journey is a slow-motion farewell within a stable partnership, not a desperate flight for freedom. This contrast is profoundly instructive. It shows that whether a moon becomes a Ploonet depends entirely on the specific gravitational architecture of its solar system. In a compact system with a hot Jupiter, tidal forces are ferocious and escape lanes are short. In our more spacious and orderly neighborhood, the same basic physics leads to a gentle, eternal drift. Our lunar companion is a testament to stability, a reminder that not every gravitational tug of war ends in divorce. The true factories for these runaway worlds are not found around small, rocky planets like our own, but in the colossal, swirling courts of gas giants. These behemoths are the universe's most prolific Ploonet producers, their very nature setting the stage for gravitational chaos. The first reason is scale. A gas giant like Jupiter is not just a planet, it is a miniature solar system in its own right. It commands a vast entourage of moons, from tiny captured asteroids to massive, complex worlds that would be considered planets if they orbited the Sun. Jupiter's four largest moons, the Galilean satellites Io, Europa, Ganymede, and Callisto, are a perfect example. Each is a unique world, with Ganymede being larger than the planet Mercury. This creates a crowded, dynamic environment where multiple large bodies are constantly tugging on each other within the planet's gravitational sphere. It is a recipe for complex orbital resonances and close encounters, the very interactions that can destabilize a moon's path. The second reason is raw gravitational power. A gas giant's immense mass creates a deep gravitational well, but also generates ferocious tidal forces. As these giant planets migrate inward through their solar systems during formation, a process we now know is common, they drag their entire satellite systems with them into hotter, more violent regions. The star's gravity grows stronger, shrinking the planet's Hill sphere, the zone where it can hold onto its moons. At the same time, the gravitational interplay between the star, the migrating planet, and the jostling moons becomes a turbulent storm. Moons can be pumped with orbital energy, their paths stretched and distorted until they are flung clear of the planet's grasp. Picture a moon like Ganymede, a vast world with a subsurface ocean, trapped in this gravitational maelstrom. In a more compact or chaotic system than our own, a moon of its size and distance could easily become a pawn in a celestial tug of war. A resonant kick from a sibling moon, combined with the growing pull of the nearby star, could provide the final nudge. Ganymede would slip over the edge of Jupiter's shrinking zone of control. In that moment, it would be promoted from a satellite to an independent world, a colossal, icy Ploonet beginning a new, solitary orbit around its sun. It would carry its hidden ocean into the deep freeze of space, a fossilized water world adrift between planets. This is not just speculation about Jupiter's family. We see gas giants orbiting extremely close to their stars all across our galaxy, the so-called hot Jupiters. Their current, quiet orbits likely hide a violent past of migration and moon ejection. The very existence of these lonely giants suggests they may have left a trail of orphaned worlds in their wake, a scattered family of Ploonets cast out during their inward journey. So if these factories are so effective, where is all the evidence? The aftermath of such a dramatic event must leave some trace. A moon's atmosphere is not just a layer of gas, it is a fragile shield held in place by a delicate balance of forces. For a Ploonet, the act of escape shatters that balance completely. The journey from a protected satellite to an independent world orbiting a star is an extreme atmospheric makeover, a process of cosmic alchemy that can create bizarre and fleeting environments. Consider Titan, Saturn's largest moon, a world often compared to a primordial Earth. It is shrouded in a thick, nitrogen-rich atmosphere denser than our own, with lakes of liquid methane on its surface. This atmosphere persists because Titan orbits safely within Saturn's powerful magnetic field, a protective bubble that deflects the worst of the solar wind, the relentless stream of charged particles from the sun. If a moon like Titan were somehow ejected to become a Ploonet, it would lose that magnetic shield in an instant. Suddenly exposed, its atmosphere faces a brutal onslaught. The stellar radiation and solar wind would begin to erode the gaseous envelope, molecule by molecule, blasting it away into space. This process, called atmospheric sputtering, could strip a world bare over millions of years, leaving behind a desolate, airless rock where once rivers of hydrocarbons flowed. But the story is not always one of simple loss. The new thermal environment of a Ploonet could trigger astonishing transformations. Imagine an icy moon, rich in frozen volatiles like water, ammonia, and methane, escaping from the deep freeze of the outer solar system and migrating inward. As its new orbit brings it closer to the star, the rising temperatures would cause these ices to sublimate, turning directly from solid to gas. For a time, this Ploonet would blossom with a temporary, shimmering atmosphere. It could sport vast water vapor geysers, clouds of exotic chemicals, and even transient surface liquids. becoming a world with seasons measured in millennia of atmospheric growth and collapse. This would be an exotic and short-lived spectacle, an atmosphere born from its own thawing heart. The composition of this new air would be a direct record of the Moon's interior, a ghostly breath revealing what was frozen deep below its crust for billions of years. Yet, without a magnetic field or sufficient gravity to hold onto these newly freed gases, this atmosphere too would eventually be stripped away by the star or lost to space, leaving behind a dormant core once more. The atmospheric fate of a Ploonet is a race between creation and destruction, between the gases released by its new warmth and the stellar forces determined to tear them away. This creates the potential for some of the most unique and ephemeral worlds imaginable, celestial bodies that are only Earth-like or active for a brief geological moment during their long, lonely journeys. This atmospheric transformation leads to an even more profound question. Could a Ploonet ever become a home? The search for life beyond Earth focuses intensely on the habitable zone, that narrow band around a star where temperatures are just right for liquid water to exist on a planet's surface. For decades, we have looked at rocky planets orbiting within this Goldilocks region. But what if the most promising candidates for life are not planets at all? Imagine an icy moon like Europa or Enceladus, worlds we know harbor vast global oceans hidden beneath their frozen crusts. These subsurface seas are locked in perpetual darkness, sealed away from the energy of their sun by miles of solid ice. Now picture that moon breaking free. Its Ploonet journey carries it inward, not into a scorching death spiral, but into a gentle, stable orbit right in the middle of its star's habitable zone. The stellar warmth that once barely kissed its icy shell now grows stronger. Over millions of years, that heat begins to thaw the global ice cap. The frozen crust melts, fracturing and retreating. The hidden ocean, once imprisoned, is finally exposed to sunlight and an open sky. In this miraculous scenario, the Ploonet undergoes a second birth. It transforms from an ice-covered satellite into a true water world, a globe-spanning ocean with perhaps only archipelagos of ancient ice or rocky core material peeking above the waves. This is not science fiction, but a plausible chain of events within the rules of astrophysics. We already have the ingredients. Icy moons with subsurface oceans are common in our own solar system. We have the mechanism. Gravitational chaos can eject them. And we know the destination. The habitable zone exists around countless stars. The result could be an entirely new class of habitable world, one born not from the dust of a protoplanetary disk, but from the great escape of a moon. The implications for life are staggering. That subsurface ocean, once dark and isolated, would have been a chemical reactor for billions of years, rich with minerals and potential energy from hydrothermal vents on the seafloor. Life, in some primitive form, might have already arisen in that deep, dark abyss, just as scientists suspect it could have on Europa. The Ploonet's migration into the habitable zone would then be a cosmic rescue mission. The thawing ice delivers that life or its building blocks to a sunlit surface ocean. Suddenly, photosynthesis becomes possible. Complex ecosystems could blossom in this new, open water. The world gains an atmosphere from the outgassing of its warming interior and from the vaporizing ice. It becomes a true twin of Earth, but with a history infinitely more dramatic. Its story would be written in the unusual chemistry of its water, a memory of its long epoch as a high-pressure subsurface sea, and in the strange tilt of its orbit, a permanent scar from its violent departure. Finding such a world would force us to completely rethink where life could take hold. The galaxy may be filled with these second-chance oceans, orphaned moons that found not just freedom, but a perfect new home under a welcoming sun. A Ploonet's chaotic orbit is more than just a path, it is a historical document. This rogue world carries within its trajectory the encrypted story of its birth and the violent adolescence of its entire solar system. To an astronomer, discovering one would be like finding a fossilized bone in a riverbed, a single piece that hints at the anatomy and life of a long-lost creature. The Ploonet is a cosmic fossil, a relic from an era of tremendous gravitational upheaval that most planetary systems experience in their youth. Its very existence is a clue, and its specific orbit is the evidence. By carefully reading this evidence, scientists could reconstruct events that happened billions of years ago, events that shaped the family of planets we see today but left no other visible trace. Think of our own solar system. We see the orderly orbits of 8 planets, a picture of calm stability, but this calm is deceptive. The craters on the Moon, the tilted axis of Uranus, the bizarre composition of Mercury, all these are scars from a wild and violent past. We believe giant planets like Jupiter and Saturn migrated inward and then outward in a grand gravitational dance, a process that would have scattered asteroids and comets everywhere, potentially ejecting smaller worlds in the process. If a moon had been torn away during that chaotic epoch, its Ploonet orbit today would be a direct recording of that ancient migration. Its elliptical path and high inclination would tell us the direction and force of the gravitational kicks it received. It would be a living witness to events we can only model on computers. In other star systems, the clues could be even more dramatic. Imagine finding a Ploonet with an orbit that is not only tilted but also retrograde, meaning it orbits its star in the opposite direction of all the other planets. Such a bizarre path is almost impossible to explain through normal planet formation. It screams of a catastrophic encounter, a near miss, or even a direct collision between 2 giant planets that sent a moon careening off on its own, flipped upside down in the process. Finding that Ploonet would allow astronomers to work backwards, like detectives recreating a crime scene. They could calculate the masses and speeds of the long-vanished planetary bodies that caused the disruption, piecing together a family portrait of a solar system that no longer exists in its original form. Even the absence of Ploonets tells a story. If we survey hundreds of star systems similar to our own and find no Ploonets, that too is critical data. It would suggest that our solar system's history was unusually violent, or conversely, that our models for moon formation and ejection are flawed. Every search, whether it finds a Ploonet or not, helps refine our understanding of how planetary families are born, evolve, and find their final, stable arrangements. These orphaned worlds are not just curiosities, they are the missing pieces to a puzzle that spans light years and eons, a puzzle about our own origins and the fate of worlds around every star. The most terrifying aspect of a Ploonet is not its own loneliness, but the chaos it can unleash upon others. This wandering world is a gravitational wrecking ball, a migration menace whose very presence can rewrite the fate of an entire solar system. Its chaotic, inclined orbit does not politely stay in one lane. It cuts across the orderly paths of established planets and the delicate balance of asteroid belts. Every close pass is a gravitational perturbation, a small but significant shove that can accumulate over millennia. A Ploonet swinging past a gas giant, for instance, could nudge that giant's orbit just slightly, which in turn alters the orbits of all its moons and the trajectories of countless comets in the outer system. This domino effect can send a ripple of instability through a once calm family of worlds. The inner planets, those small, rocky worlds like our own Earth, are especially vulnerable. A Ploonet's path could carry it through the main asteroid belt, the ring of rocky debris between Mars and Jupiter. Its gravity would act like a shepherd stirring a flock, scattering asteroids from their stable orbits. Many of these perturbed rocks would be flung onto new, dangerous paths, some spiraling inward toward the star. For any Earth-like world in that system, this could trigger a cataclysmic period of bombardment, a rain of fire not seen since the system's violent birth. Imagine a planet with burgeoning oceans and a thin, new atmosphere, a potential cradle for life, suddenly facing a million-year barrage of city-sized asteroids. The Ploonet, long gone on its elliptical journey, would never witness the devastation it initiated, leaving behind only craters and extinction as its calling card. In a more direct and final scenario, the Ploonet's path could intersect with another planet's orbit at exactly the wrong moment. The result is not a near miss, but a head-on collision of unimaginable scale. This is not a small impact like the one that doomed the dinosaurs, but a merger of worlds. A Ploonet the size of Mars striking an Earth-sized planet would utterly reshape both bodies, melting their crusts and mantles into a single glowing sphere of magma. The debris from such an impact might coalesce into a new, larger world, or form a spectacular ring system around the star. The original identities of both the planet and the runaway moon would be erased forever, fused into a single hybrid testament to gravitational chaos. In this light, a Ploonet is not just an orphan, it can be a harbinger of doom, a random element of destruction that turns a stable, life-friendly system into a shooting gallery or a cosmic crime scene. Its great escape can become the final sentence for other, innocent worlds. These celestial crime scenes are reconstructed not with chalk outlines but with lines of code. To understand the violent birth of a Ploonet, astrophysicists turn to the most powerful tool at their disposal, the supercomputer. These machines perform digital experiments that would be impossible in reality, simulating the gravitational dance of entire solar systems over billions of years in a matter of days or weeks. The challenge is immense. They are not modeling 2 or 3 objects, but a full N-body system, where every single moon, planet, and asteroid exerts a tiny gravitational pull on every other object. It is a cosmic web of influence where a small nudge on one side of the system can, over millennia, cause a catastrophic ejection on the other. Scientists start by building a virtual solar system, populating it with a star, a migrating gas giant planet, and a family of moons. They set the initial conditions, the masses, the orbits, the distances. Then they press play and let the laws of physics, encoded into their algorithms, take over. The simulation runs forward in accelerated time, calculating the gravitational tug between every single object at every moment. They watch as the planet migrates inward, its path dragging its moons along. They observe the growing influence of the star's gravity, the chaotic resonances that build between the moons, and the slow, inevitable stretching of orbits. The goal is to see if, under these intense pressures, any of the moons cross that critical threshold, the edge of the planet's Hill sphere, and break free. The simulations do more than just prove escape is possible, they reveal the escape routes. Some moons are gently nudged outward by tidal forces until they quietly slip away. Others are victims of sibling rivalry, where one moon steals orbital energy from another, flinging it out of the family in a gravitational slingshot. The most dramatic results show moons that are violently ejected after a close encounter with another large body, sent careening on wild, elliptical paths. Each simulation run is a unique story, a what-if scenario for a different solar system. By running thousands of these digital experiments, varying the starting positions and masses each time, scientists can map the most likely conditions for creating Ploonets. They learn that a gas giant migrating very close to its star is a prime factory for these orphans. They see that larger moons are more likely to be ejected than tiny ones. This virtual testing ground is how the Ploonet hypothesis moved from a curious idea to a serious, testable theory. But the true power of these models is predictive. Once a simulation produces a Ploonet, the scientists can analyze its virtual afterlife. They track its new orbit around the star. Is it highly elliptical? Is it tilted? They calculate its temperature and model what might happen to its atmosphere or icy surface. From this data, they generate a list of observational signatures, a fingerprint for telescopes to search for. The simulations might predict that a Ploonet from an icy moon will, for a time, have a giant coma of water vapor around it as it thaws. They could suggest that the parent planet, after losing a large moon, will be left wobbling on a tilted axis. These are the specific clues that turn a vague search into a targeted hunt. The supercomputer's digital universe becomes a guidebook for our real one, telling us exactly what to look for in the starlight. The search for these runaway worlds has already turned up a handful of promising and deeply puzzling candidates. While no Ploonet has been officially confirmed, astronomers are sifting through mountains of data from telescopes like Kepler and TESS, finding signals that refuse to fit into any neat planetary category. One of the most compelling hints comes not from a solid object, but from a ghostly shroud of dust. Around a star called Fomalhaut, about 25 light-years away, astronomers observed a brilliant, narrow ring of debris. This ring itself was not unusual, but its location was. It orbited far from the star, and crucially, it was offset, not centered on Fomalhaut itself. The leading explanation was that an unseen planet, shepherding the dust with its gravity, was pulling the ring off-center. Yet, despite intense searching, that planet proved elusive. Could the shepherd be a Ploonet, an escaped moon, perhaps one with a residual dusty atmosphere or one that suffered a recent collision? Could explain both the ring's sharp structure and the difficulty in spotting a clear planetary signal. It would be a world hiding in its own debris, a fitting disguise for an orphan. Another tantalizing clue emerges from the phenomenon of orphan transits. These are single, deep dips in a star's brightness that never repeat. Most planet hunters discard these as glitches, perhaps a passing asteroid or a flaw in the data. But what if some of them are the signature of a Ploonet on a wildly long, elliptical orbit? Imagine a world that takes decades or even centuries to complete a single journey around its star. Our telescopes might only catch one transit in a human lifetime, a single, mysterious blink and then nothing. Distinguishing such an event from a one-time cosmic accident is incredibly difficult, but it means the evidence for Ploonets could already be buried in old data, waiting for the right pattern recognition algorithm to uncover it. Then there are the strange infrared excesses. Some stars show unexpected warmth in infrared light, a sign of circumstellar dust that should have fallen into the star or blown away long ago. This dust needs a source to replenish it. A Ploonet, especially a fragile, icy one drifting into the warmer inner system, could be that source. As its surface sublimates, it would continuously feed a cloud of fine particles into orbit, creating a persistent, dusty glow that telescopes can detect long before they see the core itself. Each of these clues is circumstantial, a shadow on the wall rather than the object casting it. The scientific community rightly demands harder evidence before announcing a discovery. But that is what makes this frontier so electrifying. The hunt is live. Every strange, unexplained blip in the data is a potential flag planted by a runaway world. Confirmation will likely require a multi-method attack, combining a faint transit signal with the subtle wobble it induces on its star, and perhaps a spectral analysis of its hypothetical dusty tail. It is a detective story unfolding in real time across the galaxy, where the next dataset could contain the clue that changes everything. The term Ploonet itself feels like a friendly wink from the cosmos. It is not a stern, Latin-derived classification from a dusty textbook. It is a portmanteau, a playful blend of planet and moon that sounds almost like a child's toy or a cartoon character. This informality is its secret strength. In the precise, data-driven world of professional astronomy, where terms like escaped satellite or orphaned moon are perfectly accurate, the word Ploonet did something remarkable. It stuck. It provided a shorthand that was not only efficient but also evocative. Saying escaped satellite describes a process, saying Ploonet tells a story. It personifies the object, giving it an identity and a narrative of motion, and change that a dry technical phrase simply cannot convey. The astronomical community, often portrayed as serious and reserved, embraced it because it filled a linguistic gap for a concept that was suddenly, urgently needing a name. When the theoretical models showed these objects could be real and important, scientists needed a way to talk about them quickly and clearly, both with each other and with the public. Ploonet was that bridge. It is a testament to how science evolves, not just in its theories, but in its language. A catchy, memorable name is not just for headlines, it is a crucial tool for public engagement. Think of terms like black hole or Big Bang. They are vivid, almost poetic handles for impossibly complex ideas. They spark the imagination first, inviting curiosity that leads to deeper understanding. Ploonet operates the same way. It takes an abstract astrophysical possibility, a moon ejected via gravitational resonance, and makes it tangible. It gives us a character to follow in this cosmic drama. A child can hear the word and instantly grasp the core idea, something between a planet and a moon. That accessibility is priceless. It transforms a niche calculation into a shared story, reminding us that the universe is not just a collection of equations, but a place of endless dynamic change, where even the definitions of worlds are written in pencil, ready to be revised by the next great escape. The line between scientific prediction and creative prophecy is often wonderfully blurred. Long before astronomers coined the term Ploonet, storytellers were already dreaming of wandering worlds and orphaned moons, sensing a poetic truth in the cosmos that science would later seek to explain. One of the earliest and most charming examples comes from a children's fable. In Antoine de Saint-Exupéry's The Little Prince, the titular character does not hail from a planet, but from a tiny asteroid known as B612. This miniature world, with its 3 volcanoes and a single rose, is a literary Ploonet in spirit, a solitary, personified chunk of matter drifting alone through space, home to just one soul. It is a metaphorical exploration of loneliness and connection, but it captures the essential image of a small, isolated world untethered from a larger system. On a far grander and more ominous scale, the film Melancholia presents a rogue planet named Melancholia itself on a collision course with Earth. While technically a planet, its sudden appearance from behind the sun and its terrifying, unstoppable trajectory embody the profound dread of a chaotic celestial body, a world that does not follow the rules, disrupting the cosmic order and spelling doom for a stable, living world. Its narrative role is that of the ultimate Ploonet, an agent of absolute change and destruction. These fictional portrayals are not accurate scientific models, of course, but they are powerful emotional and philosophical explorations of the concept. They ask what it means for a world to be adrift, what happens when the sky contains a stranger, and how fragile our sense of cosmic order truly is. Video games, too, have embraced the drama of runaway worlds. In the cosmic sandbox of Kerbal Space Program, ambitious players have engineered the ultimate challenge, using gravitational slingshots to literally rip moons from their orbits and send them careening toward the sun or into deep space, a playful simulation of the very forces astrophysicists study. These creative works do more than entertain. They shape the imagination of future scientists and the public, making the strange plausible. They prepare our minds to accept that the universe might be wilder than our textbooks, that a moon could indeed run away from home. Art does not just reflect science, it often runs ahead of it, dreaming up possibilities that rigor later tests. So when we now look at a strange day to point from a distant star and whisper, "Could that be a Ploonet?" we are joining a conversation that began not in a lab, but in the human heart's fascination with lonely things in the dark. A new era of discovery is now opening with an instrument of unprecedented power, the James Webb Space Telescope. While previous searches relied on faint dips in visible starlight, Webb operates in the infrared, seeing the universe in the glow of heat. This changes everything for Ploonet hunters. These orphaned worlds, especially those that have drifted far from their star, are cold and dark, emitting almost no visible light. But every object with mass retains some warmth, a faint thermal signature from its formation or from radioactive decay in its core. Webb's exquisite infrared sensors are designed to detect precisely this kind of faint, cold glow. It could potentially pick up the heat of a lone Ploonet drifting in the outer reaches of a distant solar system, a solitary speck of warmth against the profound cold of space. Even more promising is Webb's ability to perform transmission spectroscopy. When a candidate object transits its star, starlight filters through its atmosphere if it has one. Molecules in that atmosphere absorb specific wavelengths of light, leaving a chemical fingerprint in the spectrum. Webb can analyze that filtered starlight with incredible precision. Imagine a mysterious object transiting a star, one with an orbit too elliptical to be a normal planet. As it passes, Webb could study the light. If it detects signs of water vapor, methane, or complex hydrocarbons, that would be fascinating. But if it finds an atmospheric composition strikingly similar to that of a moon like Titan, rich in nitrogen and methane, the evidence would become compelling. That chemical signature would be a direct link, a ghostly echo of the object's origin as a satellite orbiting within a giant planet's protective embrace. Webb offers the chance to move from spotting strange shadows to taking a celestial object's fingerprint, potentially providing the first concrete, undeniable evidence that we are looking at a world that once belonged to another. The sheer scale of the galaxy makes this a numbers game of staggering proportions. To estimate how many Ploonets might be drifting through the Milky Way, we must first count the raw ingredients, the planets and moons that serve as their factories. The Kepler mission revolutionized our understanding, revealing that planets are not rare. On average, nearly every star in our galaxy hosts at least one planet. With over 100 billion stars in the Milky Way, the baseline population of planets is already in the hundreds of billions, but the real multiplier is moons. In our own solar system, for every one planet, there are dozens of moons. The 4 gas and ice giants alone account for well over 200 confirmed satellites. If this ratio is even remotely typical, then the galaxy is not just a sea of stars and planets, but an ocean of moons, a vast reservoir of potential Ploonets waiting for the right gravitational trigger. Statistical models built on these observations paint a picture of surprising abundance. Astrophysicists run simulations that incorporate the rates of planet migration, the stability of moon systems, and the chaotic dynamics of young solar systems. The results consistently suggest that the process of moon ejection is not a freak accident, but a standard part of planetary system evolution, especially around the most common type of star, the red dwarf. One influential study estimated that between 3 and 5% of all moons around giant planets could be ejected over a system's lifetime. That percentage might sound small, but when applied to a galaxy containing trillions upon trillions of moons, the math becomes profound. It points to a population of Ploonets that could easily number in the tens of billions, potentially rivaling or even exceeding the count of traditional, star-orbiting planets in the Milky Way. This shifts our cosmic perspective entirely. We have long pictured solar systems as neat, nested hierarchies, a star with planets and those planets with moons. But if Ploonets are as common as the models suggest, that tidy image is incomplete. Our galaxy is not just a collection of orderly families, it is also filled with wanderers, a vast diaspora of worlds that left home. These nomadic orbs would fill the spaces between the classical planets, on orbits tilted every which way, tracing silent, lonely paths that cross the well-traveled lanes of more settled worlds. They are the galactic background population, the cosmic nomads whose histories are written in orbital scars rather than in a stable address. The implications of such a crowded nomadic population are transformative for how we search for life and how we understand cosmic history. First, it massively expands the real estate for potentially habitable environments. As we discussed, an icy moon ejected into the habitable zone becomes a thawed ocean world. If Ploonets are exceedingly common, then so too are these second-chance water worlds. The galaxy's total number of habitable environments could be far greater than a simple count of rocky planets in the Goldilocks zone suggests. Life might find its most frequent foothold not on primary planets but on refugee moons. Second, this hidden population acts as a cosmic record. Each Ploonet is a fossilized piece of evidence about the chaotic early days of its home system. By studying their collective orbits and compositions, we could statistically reconstruct the violent migration histories of giant planets across the entire galaxy, reading a story of gravitational upheaval that has largely faded from view in mature systems like our own. We would come to see our calm, orderly solar system as the exception, and a galaxy humming with the quiet motion of orphaned worlds as the rule. A Ploonet's solitary journey may last billions of years, but even its independence is temporary against the cosmic clock. Every star has an expiration date, and when that final chapter arrives, the entire solar system is rewritten. Our own Sun, now a stable middle-aged star, will one day exhaust the hydrogen fuel in its core. In roughly 5 billion years, it will swell into a monstrous red giant, its outer layers expanding to engulf the orbits of Mercury, Venus, and likely Earth. This stellar metamorphosis is the ultimate test for any surviving Ploonet. For one orbiting close to its star, the fate is swift and absolute. As the star's atmosphere bloats outward, the Ploonet would plunge directly into this tenuous but searing hot envelope. It would not be swallowed whole like a planet might be. Instead, it would experience a relentless fiery drag. The Ploonet would spiral inward, its orbit decaying with each pass, superheating until its surface melts and its very substance is vaporized and scattered, adding a faint whisper of metals to the star's expanding shell. Its long story of escape would end in total dissolution. Its atoms return to the stellar furnace from which its original planet first formed. But a Ploonet orbiting farther out might witness the cataclysm from a safer distance. As the star loses mass during its red giant phase, its gravitational grip on the entire system weakens. Orbits relax and widen. A Ploonet could find itself gently pushed outward, its elliptical path growing even larger as the star at its center transforms. Then the star sheds its outer layers entirely, creating a beautiful planetary nebula, and leaves behind only its incredibly dense, Earth-sized core, a white dwarf. This is the stellar remnant that will glow faintly for trillions of years. The Ploonet would now orbit this tiny, brilliant cinder. Its new environment would be one of profound quiet and cold. The white dwarf emits little heat, so any temporary atmosphere the Ploonet gained would freeze solid, collapsing back onto its surface as a permanent frost. The world becomes a frozen fossil, a dark and silent monument to a solar system that once was, circling a ghost of its sun. There is a third, more dramatic possibility. The violent process of a star shedding its mass is not perfectly symmetrical. This uneven loss can give surviving objects a gravitational kick, like a boat rocked by a sudden, one-sided wave. A Ploonet already on a precarious path could be the recipient of such a nudge. If the kick is strong enough, it could break the weakened bond with the white dwarf entirely. The Ploonet would be ejected not just from its planetary family, but from its stellar system altogether. Its long migration would culminate in the ultimate exile, becoming a true rogue object in the interstellar medium. It would wander the galaxy forever, untethered to any star, its only warmth the negligible heat from its own radioactive core. In this final form, the Ploonet completes a tragic arc from a moon bound to a planet to an independent world orbiting a star, and finally to a lonely wanderer in the endless dark between suns. This ties the Ploonet saga directly to the grand life cycle of the cosmos itself. Its fate is a direct reflection of where it was when its star began to die. Its story becomes a single thread woven into the epic narrative of stellar evolution, from the furnaces that forge heavy elements to the cold, dark fade of white dwarfs. The existence of Ploonet suggests that even in the final, fading glow of a star system, there may be silent, frozen witnesses orbiting the remnants, carrying the last memories of a once vibrant family of worlds. This transforms the search for life into a hunt for cosmic refugees. If Ploonets are common, then the galaxy's most promising cradles for biology might not be traditional planets at all. They could be these escaped oceanic moons, thawed and transformed under a new sun. Our own solar system offers a blueprint. Europa and Enceladus are frozen worlds with global saltwater oceans hidden beneath miles of ice, kept liquid by the gravitational squeezing of their giant planets. Scientists believe these dark, pressurized seas, rich with minerals from hydrothermal vents, could be perfect incubators for microbial life. Now grant that moon its freedom. Imagine a gravitational nudge sends it spiraling inward, not into destruction, but into a stable orbit within its star's habitable zone. Over millennia, stellar warmth penetrates the icy shell. The global cap fractures and melts. For the first time in billions of years, that hidden ocean sees sunlight from above. The chemistry that was brewing in perpetual darkness is suddenly bathed in energy. This is not merely finding a new home, it is a world experiencing a second birth. The implications for astrobiology are staggering. It means life could arise in two distinct phases. Primitive organisms, or at least their complex chemical precursors, might have already formed in that deep, subterranean sea during the moon's original orbit. The Ploonet's migration then becomes a cosmic delivery system, transporting a pre-packaged experiment in biology into an environment where it can truly flourish. Photosynthesis becomes possible. An atmosphere develops from outgassing ice and volcanic activity. Ecosystems could explode in complexity in this new, open water. We are not just looking for Earth twins anymore. We are searching for worlds with a hidden ocean in their past, a geological memory that makes them uniquely fertile. A Ploonet biosphere would be built on a foundation of extremes. Its life would be descended from organisms adapted to total darkness, immense pressure, and a chemistry built around methane or sulfur, not oxygen. When that ice cap opened, it would have been the greatest ecological revolution in that world's history, a shock far more profound than any event on Earth. The life that emerged into the sunlight might be utterly alien in its biochemistry, a blend of deep-sea resilience and new photosynthetic potential. Finding such a world would force us to rewrite the rules of what life requires. It tells us that the galaxy's most habitable real estate may not be prime planets, but second-chance moons, orphaned worlds carrying the seeds of their own awakening across the solar system. Their great escape becomes life's great opportunity. A moon's escape is a story of cosmic chaos written in gravity and ice. We have traced its journey from a stable orbit, bound to a planet in an ancient dance, to a rogue Ploonet drifting alone around its star. The forces behind this great escape are both subtle and violent, from the relentless tidal pull of a star slowly stretching an orbit, to a catastrophic gravitational kick from a passing world that flings a moon into the abyss. The destination is a lonely independence, a chaotic path that can lead to fiery destruction, eternal exile, or a miraculous second chance in the habitable zone. Finding these orphans requires looking for the clues they leave behind, the strange shadows in starlight, the unexplained dusty rings, or the single, non-repeating transit that hints at a century-long orbit. Their existence, if confirmed, would do more than add a new category to our celestial charts. It would force us to acknowledge that our galaxy is not a static museum of orderly worlds, but a dynamic, often violent arena where moons can run away and planets can lose their children. It blurs the very line between a moon and a planet, revealing that a world's identity is not permanent, but a temporary state in an endless gravitational drama. Most profoundly, it redefines the search for life itself, suggesting that the most promising cradles for biology may not be traditional planets at all, but these refugee oceans thawed under a new sun and carrying the seeds of a second Genesis. So the next time you look up at our own moon, hanging in its familiar silence, consider its impossible journey. It is a story of quiet retreat, not escape, but out there in the dark, countless other moons may have taken that leap. They are the nomads, the orphans, the Ploonets, each a silent testament to the beautiful, chaotic, and ever-changing nature of our universe. And with every new telescope pointed at the sky, we get closer to finding the first one, to hearing its story, and to understanding our place in a cosmos far wilder than we ever dreamed.